We live on the cutting edge of physics, material science, engineering, and nanotechnology. Because at Lockheed Martin, we're engineering a better tomorrow.
Greetings from the International Space Station. I'm NASA astronaut Drew Feustel, along with my colleague, NASA astronaut Ricky Arnold. As we orbit the Earth at a speed of 5 miles a second, we're constantly awed by the amazing fact that this facility supports world-class science in so many unique ways.
Every day, Drew, I, and our crewmates are conducting research in areas like life and physical sciences, technology and engineering, the study of the planet below, and learning how the human body can live in space for long periods of time. Another critical function of the space station is to engage and excite the next generation of scientists, researchers, and explorers. During the USA Science and Engineering Festival, you will hear from representatives of NASA and CASIS who can provide further information on how young students can become space station explorers. We encourage you to learn more about this orbiting laboratory that we are lucky enough to call home.
On behalf of NASA and CASIS, we want to thank you for being part of this event and encourage you to dream big and look to the stars. All the best to you from all of us on the International Space Station.
Good afternoon, everyone. How are you? Welcome to the 2018 USA Science and Engineering Festival. Everybody having a great time? Seeing some cool stuff? That is awesome. That is awesome. Thank you for joining us here today. My name is Ken Shields. I'm with the ISS National Laboratory, the International Space Station's U.S. National Laboratory. I work with a nonprofit research center that's called the Center for the Advancement of Science in Space. We manage this national laboratory. You heard me right, it's in space. This is a laboratory in space that is hosting all sorts of different kinds of investigations, science projects, innovations in technology that you just heard our crew members from the ISS tell you about. It's a fantastic place to work. It's also a place where we have a little fun, particularly in the STEM education world. We're going to learn a little bit more about that today. Let's start with talking a little bit about the International Space Station. Does anybody know where it is? Where is it? It's in space. That's a trick question. Sometimes people fall for that. So the International Space Station is about 250 miles of altitude above the Earth. It orbits the Earth once every 90 minutes or so. So in a 24-hour period, our astronauts and our cosmonauts get the pure luxury and opportunity and beauty of viewing 16 sunrises and 16 sunsets in a 24-hour period. That's pretty cool. In addition to that, you think about the International Space Station, goes around the world in an hour and a half. That's really fast. So the ISS travels at a speed of a little over 17,000 miles per hour. What does that mean, 17,000 miles per hour? That just blows my mind. It's about every second, almost 5 miles. 5 miles. Think about that, kids. Boom, you just went 5 miles. From Washington to D.C. and Washington, D.C. to Los Angeles, about 9 minutes. 9 minutes. I travel a lot. That's first class. I'd love to have that opportunity. So a little bit about the ISS and how it was built. They started construction, the international partners, including the U.S., we started construction on the ISS in 1998. The first segment of the ISS was actually the Russian segment, Zarya, which means dawn. It took us 13 years, about 100 missions, over 100 missions, maybe around 115 launches of different vehicles into space to assemble the ISS. Something that's really important, no doubt, the ISS, the International Space Station, it's the most amazing engineering marvel in the history of mankind. You think about this thing, it's the largest man-made object in orbit. Most of all of the pieces that you see on the ISS, they came together for the first time in space. We had pieces that were made in Europe. We had pieces that were made in Texas. We had pieces made in Alabama, Florida, all taken up separately and joined in space for the first time. That's some serious engineering. It's about the size of a football field. If you took it and you brought it down to Earth and you laid it down on the surface of the Earth, it would fill up a football stadium. Inside, volumetrically speaking, it's about the size of a 6-bedroom house. And there are some creature comforts. We have a gymnasium, we have a galley, a couple of bathrooms. That's always a fun question to answer about bathrooms in space, but that's a different talk. We're not going to get into that here today. So the ISS was completed in about 2011, and our organization manages the National Laboratory. What we do at the National Laboratory, we do science in space to benefit life on Earth. NASA's using the ISS to understand how to live in space longer, travel in space farther. Someday we're going to be on the moon, Mars, other places, and we're solving problems by living and working on the space station. Our organization, we lead investigations and projects on the ISS to help us here on Earth. So we're working with all sorts of government agencies and academia and companies on things like better drug development, better product formulations for things that you have in your home that you use every day, and even for STEM education. We've got a number of STEM programs, and you can learn a lot about them. We have a booth over here, CASIS. Go over there. We've got a lot of fun things to do and programs to learn about. And the ISS, probably my favorite, is it's a great place to sit and look back at Earth. And the one thing you hear from ISS crew members and astronauts that go to space is that's a real impact on them. When they look back at Earth, there's no borders. It's just a beautiful blue planet in the middle of this dark blackness, and it's our home. It's all of our home, and there are just some fantastic pictures and imagery and sensing that we do from the ISS that's not only visually pleasing to look at and a lot of fun to view, but we use them for a lot of Earth science applications to improve life on Earth. So with that, we've got some very special guests, some researchers here today that I'd like to bring up and introduce to you. Our first guest is a sophomore at Yale University. She has been involved with space station research and a few STEM programs. She's studying biophysics and biomedicine at Yale. She's a sophomore. It's my pleasure to bring up Sofia Bagirayev.
I'm Sofia, and I like to call myself a girl with a box. This is my box. This is a picture of me holding my box. But what this box was, for me, was a way to become involved as a student with all of the really cool research that's going on the space station. Of course, though, this box, the one I'm holding, it's pretty complicated. It's a really sophisticated piece of technology. It's called a PCR machine. That means polymerase chain reaction, and it's this machine that you use when you want a little piece of DNA. You take that DNA and then you put it in this machine, and this machine is going to make loads and loads of copies of it. It's a pretty standard technique in labs on Earth, but it had never been done in space before. And this box enabled that. But long before I was a girl with this box, I was a 4-year-old, and I was at home, and I made myself rocket ships out of cardboard boxes. I had, much like the American Girl doll, this year's doll of the year, I had an American Girl doll, and I would make her astronaut costumes. I loved to stare at the stars. I always dreamed of space, but it seemed so distant. What can a kid do to, actually get to space, actually have things happening on the space station, be involved with this research? But then, my junior year of high school, I came across this competition called Genes in Space. Genes in Space is a competition for students in grades 7 through 12 that allows them to design their own DNA experiment to be run on the space station. It's a very easy competition to enter because it asks for no technology. It doesn't ask for you to do experiments beforehand. All you need is an idea. And on the website, www.genesinspace.com, you go and you submit that idea. And you write out, hey, I have this really fascinating idea about, what happens to my DNA in space? What happens to the DNA of different animals, different organisms, and we send them to space? Maybe mice, maybe bacteria. What can that tell us about life in space? And the Genes in Space program lets you write that up, and then they select a team of, or 5 teams of finalists, and those finalists get help from mentors to refine their experiment into something that's actually practically doable on the space station. This is a competition anyone can enter. And when I saw this, it was mind-blowing. I was like, wow. This isn't, a really fancy grant proposal that only scientists can pull off. This is something that is for me as a kid. They want my ideas. My ideas have value, and that's something that I don't think you hear enough in science. You hear about, all the old men and women doing their science and finding these great things, but when do you hear about the science the kids are doing? But Genes in Space enables that. And just to tell you a little bit about my experiment, I want to help show you how things might seem complicated, but they're actually really simple. So this is one of the first slides from the presentation I ended up giving at the International Space Station Research and Development Conference, which is where the final round of the Genes in Space competition is held. Of course, at this point, I had worked with many mentors, I had worked with many people who had helped me go from this really, really general idea I had at first. At first I said, okay, so you want me to do an experiment with this box, with this PCR machine. What am I going to do? I care about astronauts' health. I want to understand how to keep astronauts healthy in space. So I want to use this box to look at their immune systems and to look at the changes in their immune systems over the course of the time they spend in the space environment. So, in more fancy words, that's what's on the slide behind me. I was basically trying to design a PCR-based assay to monitor epigenetic changes in astronauts. But in spite of the fancy words, it's an idea that anyone with enough excitement and enthusiasm can come up with. They want ideas, not fancy science jargon. And they want you to have a passion, and they want you to follow that passion. So I went on, with the help of all of the scientists I work with, to explain certain techniques I would use. This is a technique called bisulfite conversion. It's just a treatment that allows you to look at DNA. People helped me understand it more. And with all of this, I was able to run an experiment on the space station. So 2 years ago tomorrow, my experiment launched on SpaceX Cargo Resupply 8 to the International Space Station, and about a week and a half after that, I got to watch as Tim Peake, one of the European Union astronauts, ran my experiment, and it was actually the first PCR-based experiment ever run in space. And that was something that was accessible to me as a high school student. What you see behind me are the results of this experiment, which were then also published in a paper that I wrote in one of the Nature partner journals, Nature Microgravity. And this is all stuff, had you asked me 4 years ago if this would have been possible, I would have laughed. Of course it's not possible. What student could do something like that? But through the Genes in Space program, I was able to do so much more than I had ever even imagined. So this is me. As you can tell, I was super excited watching the launch. Who wouldn't be? But that's not even the greatest thing I got out of this experience. I also got the opportunity to do world-class science. I got the opportunity to talk to professional scientists in both space and biology, both as teachers and as peers. They wanted to listen to what I had to say, to the ideas that I had. I got to work with other students involved in not only the Genes in Space program, but other students involved in the other CASIS science programs. And I got to meet some really cool people like astronauts, which, who doesn't want to meet an astronaut? So what is really important, and what I learned as, me and my box that went from being that cardboard box I played with as a 4-year-old to a piece of technology I can hold in my hand that had my ideas in it and launched to the space station, is that literally the sky is not the limit. There's so much you can do, and you don't need, 45 years of education, hundreds of years working in science labs to do it. You can do it now. You can do it with an idea. If you're really interested in the Genes in Space program specifically, it runs every year. This year's Genes in Space program submissions close on April 20th, so you do still have a few weeks if you want to submit an idea, and you can submit ideas year after year after year. So I fully encourage you, if you're at all interested in biology and space, to look into this, to look into how you can take your ideas, how you can take your dreams, how you can take those hopes you feel when you look at the stars and make them something tangible. Because that's all I did. I just had a dream. I had an idea, and I was a girl with a box. So what's in your box? It can be anything. You're limited only by your capacity for awe and the bounds of an infinitely expanding universe.
Thank you, Anna Sofia. That was awesome. You want to put your box up here with the other experimentation devices? Let's hear it one more time for Anna Sofia. Nice job. We're so proud of Anna Sofia. Genes in Space is a fantastic program. It's really a great example, a shining example of the types of programs and curriculum that you can access via Space Station Explorers with CASIS and the ISS National Laboratory. By the way, all of you today, by being here, you are now officially Space Station Explorers. So welcome, and thank you for joining us on this journey. We've got several special guests. How many people in here watch Nickelodeon? Anybody? Nickelodeon's pretty cool. So we've got an awesome guest today, and I want to ask one more question. How many people have walked around here and seen some androids or robots or drones, things like that? There's technology all over the place. That's great. So we've got a special guest. Today we have from the hit Nickelodeon TV show, I Am Frankie. Welcome to the stage, Miss Alex Hook.
Hello.
Hi, Alex.
Hello.
How are you?
Good. How are you?
Welcome. Great to see you.
Awesome. Thank you for having me.
Thanks for being here. You having a good day?
Of course I am.
What have you been doing around the show today?
Oh, well, I've been to a couple of the amazing booths over here, checking out all the science, all the androids, all the legit robots. So that's pretty cool. Been seeing some awesome faces. So yeah, just hanging around.
That's awesome. So on I Am Frankie, you play an android, correct?
Yes.
So what's that feel like? How do you prepare to be an android? How do you act like an android?
Well, actually, you know, I've had to go to some Star Trek, Star Wars type things to get some inspiration. I've looked at how people really, you know, transform from their usual selves into more of a stoic, monotone character. So yes, of course, exactly. So I've gotten a lot of inspiration for that. I really had to mold Frankie into someone, you know, that's a little different and out of character, you know, out of the norm. So yeah, it's all practice and developing who she is.
So I'd be interested to know, were you attracted to the role because you had some interest in science and technology, or maybe you taking on the role, has that garnered some additional interest from you in science and technology?
Yeah, I mean, I would have to say both. It was definitely, it caught my eye when I first saw the description of her. I definitely thought, this is so cool. I can, you know, it's a spin on what you see every day. You see these normal teenage characters. And since Frankie just looks like you and I, of course, on the outside, she's different on the inside. So she's wired differently, of course. So yeah, I just thought it'd be great for me to play around with that, and learning the character more has gotten me more interested in robots, androids, science, all the above. Yeah.
That is so cool. Well, I bet walking around here today you're going to get some good ideas about android, what an android should look like, talk like, walk like, right?
Right, for sure.
That's awesome. Well, I think I've already talked a lot about CASIS and how much at the National Laboratory we're all about science and technology and advancing innovation. And Nickelodeon, they've got quite a bit of science going too with some pretty cool stuff that they call slime. Does anybody know what slime is? Anybody seen slime?
Yeah.
That crazy non-Newtonian fluid? We've got some right here on the table. What do you say we do some experimentation with some slime, Anna Sofia?
Let's do it.
Let's do it. I might get dirty, so I want to put this thing on.
Right, you never know.
You guys didn't bring one, so you're on your own.
Uh-oh. Every man for themselves when you're doing
You got to
this
learn,
slime.
right? All right. So the first test we're going to do,
Here, do you want
we're going to do some
Go.
relatively simple, I hope they're simple, fluid physics demonstrations, right? I'm going to call this first one the floating astronaut experiment. This is a little astronaut. I don't know if you can see it in the back. I promise it's an astronaut. We're going to put him in our vessel here, which is going to kind of serve as our non-Newtonian fluid swimming pool. You want to put the astronaut in there?
Yep.
You want to do the honors? Might need a little shove. He doesn't want to go.
And we're launching.
He's in. He's in. All right. So what we're gonna experiment with today. This is our slime. Do you want to do the honors of pouring the slime?
Do I ever?
Wow. So we're going to see if the astronaut will sink or swim in slime. You guys have any idea what might happen there? Think he'll sink because this is non-Newtonian stuff. It's thick, it's gooey, it's yucky, right? So we're going to see what's going to happen. Let's try to pour it in there,
Alrighty.
Alex, if you will. Let's see what happens.
Try not to make a mess
Oh,
here.
make a mess. Don't worry about
All
it.
right, say when.
The slime is going in. Oh, no. Whoa, whoa. Hey, keep going. Let's keep going. Let's see what happens. I think he's swimming.
Hey.
All right, let's see what happens there. Very cool. So
Look at that.
far, our astronaut is actually swimming, floating, even in the non-Newtonian fluid. So I think what we're observing here is buoyancy.
Yeah, sounds right.
Sounds good to you, right? Sounds good to me. Let's see what happens, though. Maybe if we turn it upside down, it won't float. I don't know. That's why we do experiments. We don't know what we don't know. Let's see if it works. It's really thick, gooey stuff.
Still swimming.
He's still swimming and floating. So I think what we've discovered here today, at least on Earth, in 1G gravity, in 1G gravity, we still have buoyancy. That is the dominating force, and we have an astronaut that's floating. That's fantastic.
Well, good
Can
for
you
that
validate
astronaut, yeah.
our conclusion?
Yep, it's swimming.
Really hanging in there.
It's awesome.
Yeah.
Now, I wonder what would happen, though, in zero gravity. You worked on space station. What do you anticipate would happen
In zero gravity,
in zero gravity?
I think everything starts floating.
Everything starts floating.
Yeah.
Okay. It does. So in 1G on Earth, buoyancy really is driven by gravity, right? So we've just learned that this little mini astronaut swimming guy, the amount of weight he is displacing is less than what the fluid represents. But in microgravity and on the space station, we have weightlessness. So he's not going to weigh anything. And the fluid's not going to weigh anything. So I would actually hypothesize that this would not happen in microgravity, that he would be stuck in this bubble or vessel of fluid.
Kind of in the middle?
Kind of in the middle.
Sounds.
And I think if we shook it up on the space station, he might move around because there are other forces at work to make him move around in the fluid. So this is a good example of the types of activities. This was a very basic demonstration, but the types of activities and serious experimentation that we do on the space station. So there are other things that we can do, and this one might be a little trickier because we already have a containment issue. So we're going to try to mix two different types of fluids. So in this bag, we've got water, which is a Newtonian fluid. No matter what you do, its viscosity doesn't change. I could squeeze that bag. It's going to remain as thick or as thin as it is, no matter what sort of shear stress I place on it. But non-Newtonian fluid acts a little crazy. It acts a little funky. Its viscosity is dynamic, and it changes with the amount of shear force that you place on it. So as a result, when we try to mix these different types of fluids, maybe different things happen. So let's take a shot at mixing up our non-Newtonian slime with our Newtonian water. Oh man, that is super cool. Can you see the slime going into the water? It's not mixing like our Kool-Aid at all, or our Gatorade or anything else that you like to mix together.
It's like oil and water, right?
It's kind of like oil and water, sort of,
Sweet.
yeah. You're right. So I think what we're seeing here is the slime, our non-Newtonian fluid, which is once again very thick, very dense, and looks to be very heavy because what? How's it interacting with the water? It's sinking. It's actually going under the water. We're not having any mixing. The two fluids are staying separated, but clearly our non-Newtonian slime is a lot heavier than the water. And so as a result, gravity here on Earth, once again, is the dominant force. It's pulling that heavier, denser, non-Newtonian fluid, which is the slime, to the bottom of our bag. And the less dense, the lighter water is remaining at the top. Now, once again, I'll pose the question to you guys. On the ISS, what do you think we would observe?
Well,
you're an android, you're a scientist, come on.
Well, if I had to guess, I don't think they would combine at all. I think they'd both kind of form into their separate blobs and not want to interact.
That seems fair to me.
Well, just float around in its own little, own little shape here and there.
I think they might just float around in their own little pocket somewhere and maybe form little bubbles. But you know what? There's one way to find out.
By doing it.
I think we should go and try to do this. What do you think?
I definitely think we should.
I think we should work with Nickelodeon and see slime in space. What do you guys think? Let's take slime to space and see what happens. We got to do these experiments for real. That's awesome. Well, guys, thanks for helping me with the experiments.
Thank you.
Thank you, Frankie.
Thank you for
Excuse
having
me.
me.
Alex.
Oh.
I am Frankie. She had me thinking she's an android.
Right.
Let's
Thank you,
hear it for
everyone.
Alex Hook. I am Frankie, Nickelodeon's hit show. Thank you, everybody. So we're going to bring up a couple more researchers, student researchers. Our next guest is a high school senior from Charlottesville, Virginia. He's going to go to, I think he has a choice of like University of Chicago, Harvard, or Yale. Some very poor choices, but the young man is I think he's going to make a good choice. It's my pleasure to introduce Stephen Newman. Stephen, come on up and join us. Interestingly enough, Stephen has two Labrador Retrievers, my favorite dog names ever, Tesla and Faraday. That's kind of cool. Stephen, welcome.
Thank you. So going to get a few questions here. How many of you like robots? How many of you like programming? And how many of you like space? How many of you want to program robots in space? You can. The Zero Robotics program is a program that allows high schoolers and middle schoolers to program robots in space. But you don't start there. You start like I did. You start by sitting down in front of a computer and just typing a few lines of code. Maybe you don't know how to code. Maybe you've never even seen what coding is before. Maybe you do. I don't know, but whatever it is, you can get into it. You just start by sitting down and starting. Teach yourself. There are manuals. Do whatever. But then, once you're feeling good about it, you can enter the Zero Robotics competition for high schoolers or for middle schoolers. And once you do, it's like the real world. Because Zero Robotics is like the real world in a way that no other competition is. It starts, again, just by meeting your team. You meet your team, and then they give you the competition. And the competition isn't a task. It's not do this thing. They give you a set of rules, and each rule, if you follow it, if you succeed in doing what it tells you to, it gives you some number of points. And whichever team gets the most points in a match, they win. So it's not a game about doing what they tell you to do. It's a game about circumnavigating the rules, figuring out how to get points when they don't want you to get points, figuring out what not to do, what to do, so that you can eke the most points out of any given game and win it. And you have to figure that out quickly, because it's like the real world. There are deadlines. From when you start to when you first have to submit code, you have 6 weeks. 6 weeks to teach yourselves how to program, how to work with the interface, how to work with your teammates on a programming project, because that's the hardest thing out there. And yet, most people do. Most people succeed in getting past that first phase. And by then, you've already developed some real-world skills. You know how to program. You know how to program with teammates. You know how to work with other people. You know how to get around the rules. And again, most importantly, you know how to work with teammates, because it's like the real world. When you get farther, you get more teammates. In the alliance phase of the competition, that's the next phase, you get teammates from around the world. You are set up with an alliance of 2 other teams. One team from another country, one team from a third country. You'll be working across 3 different continents, 3 different time zones, probably 3 different languages. That's happened to me every year so far. And so what that means is you have to work in the real world. You have to know how to overcome those challenges, work across language barriers, figure out how to work with people in different time zones. And at the end of the day, you'll probably succeed because the program is designed for you to succeed. And so after this phase, there are half of the teams that advance, half of the teams that don't, but either way, you'll have developed those skills. You'll have developed the real world skills that you need to become an engineer next year or to do the competition again next year. And say you do advance. Say you make it to the next phase. Congratulations. You've made it to the finals. You are going to be one of the teams that has your code run on a robot on the International Space Station. But it doesn't happen just yet. You have 2 more weeks. And again, it's like the real world. It's a final deadline. You're rushing. You haven't done enough. You always have more that you want to do. You want to get rid of all the bugs in your code. You want to get those last little bits of features in so that your code can beat every other team out there. And it's not easy, but you're going to try anyway. And so say you do. You take those 2 weeks. You work every second of every day. Or it's finals week, so you don't get a chance to work. But either way, at the end of the 2 weeks, you submit code with your alliance. And then you wait, because it's over. You've done everything that you can do to affect the competition, but the competition itself isn't over, because you haven't seen the results. So you wait. You wait for a week. You wait for 2 weeks. You wait for maybe 3 weeks. And then in early or mid-January, you get a call. And that call is from MIT or CASIS or NASA. And what it says is, come down to MIT. Come to the auditorium, and come soon, because we know when we're running your code on the space station, and it's happening soon. So you go. You have a week's warning, maybe 2. You book train tickets. You book plane tickets. You figure out which of your team members can drive, who's going to drive you down there. And so you get there. You get there on a Friday night, and you're ready to go. You're so pumped. You're so excited. I know I was excited when I first went there. It was the best experience of my life. I knew the next day was going to be incredible. I was so excited that I didn't get to sleep until 3 p.m. And then I had to wake up 2 hours later. The morning of the competition is not what you'd expect. You get up at 5 a.m. sometimes. It's incredibly cold. It is way colder than you would ever expect it could possibly be. It's Boston. It's windy. You're walking through the streets at 5:30 a.m., barely awake. And then you get to MIT, and you sit down in the auditorium. And if you're like me, you almost fall asleep. But either way, whether you fall asleep or not, eventually you shake yourself out of it, get yourself back together, and you look around. And all of those moments in the past where you thought, I'd never get here, I'm not good enough to make it here, you think all of those again. Because in front of you, you see an astronaut, and they're talking to you about your code that you wrote. And then you look on the screen, and there are more astronauts. And they're floating, and you realize it's because they're on the space station, and they're talking to you, and they're running the code you wrote on robots on the space station against other teams. And so once you're there, you think, how am I here? Why am I here? What is all of this going around me? I'm just a high schooler. I'm just a middle schooler. And what you have to remember is everyone thinks like that. Everyone is up there. Everyone is there thinking, seeing the astronauts, seeing the astronaut in front of you who you can meet and talk to, a real-life astronaut, and they're thinking, how did I get here? Why am I here? And what that means for you is that if that's what you're thinking now, that this looks great, but that you could never do it, you're wrong, because everyone thinks that. Everyone thinks that at the start, and yet the people who try, some of them make it. Many of them make it. Sometimes we have as many as a quarter of the teams in the competition get up there, get to talk to the astronauts, get to watch their code run. You can be that team. And it's easy to start. There are no barriers to entry. Go to that website. Sign up. It's free. If you want to sign up, I encourage you to do it. If you have questions, feel free to email me there. And I hope to see as many of you as possible at finals next year. Thank you.
Stephen, that was awesome. Thank you very much. Really very, very inspiring and just very, very cool. I mean, 2 very, very inspiring messages there from both Anna, Sofia, and Stephen. I think one of the things that I take from both of those talks, and I hope you did as well, you just have to start, right? You just have to start. You have to give your chance the opportunity to do these things, But to get there, you got to toe the line. That's what I call it. Toe the line and get started. And this building is full of those opportunities. So get out there, learn about what they are, and get yourself started. Toe that line. So we're going to bring up another student researcher. She is a junior at the University of Chicago, speaks fluent Russian. She's looking at space policy for the future, and she's also a pretty darn good scientist who has flown a couple of payloads on the International Space Station. It's my pleasure to introduce Rachel Lindbergh from the University of Chicago, who loves chocolate alligators. Who doesn't love a chocolate alligator?
Thanks, Ken. Thank you, I need this. Hi guys, my name is Rachel Lindbergh, and I'm a third year at the University of Chicago and a student microgravity researcher for the Student Spaceflight Experiments program. Let me first tell you very briefly about SSEP. SSEP is a program of the National Center for Earth and Space Science Education and the Arthur C. Clarke Institute of Education nationally. And SSEP is a very authentic window into science. Students write their own proposals, collaborating with their peers and doing their own research. They're selected by a nationally ranked board of educators, scientists, and engineers. They send their own experiment to the space station and are then invited to present with their peers at the Smithsonian Air and Space Museum at the SSEP conference. And that combination of aspects, we call them student researchers and student scientists, but they're real researchers and real scientists. This is one of my favorite photos to show because this is the Endeavour parked at the ISS, and there are 16 student experiments on board. I think that's incredible. There are about 87,000 students who are immersed in microgravity research through this program, which represents about 19,000 proposals with 206 experiments flown to the International Space Station. So I'm in a group of students that we affectionately call the Tin Whiskies, and we're from Palmetto Scholars Academy in South Carolina. I have two partners, Joseph Garvey and Gabriel Voigt, and our experiment is on the development and detachment of tin whiskers under spaceflight conditions. So tin whiskers are a small, crystalline, electrically conductive structure, and they'll grow in circuitry, and they can cause very catastrophic failures, ranging from missiles to satellites, and honestly, your phone might even have some whiskers in it right now. And no one can tell you exactly what causes these guys to form. And you can see here how small they are. This one is just 2 microns thick. That's much, much smaller than even your hair. And the danger of them is represented in this photo on the top left. This whisker has bridged a component and could easily have caused a failure. Our experiment is using copper beryllium card guides from the Space Shuttle Endeavour given to us by our mentors at NASA Goddard Space Flight Center. That's Ludmila Panashenko, Dr. Henning Leidecker, and Jay Broussais. And these card guides have been in space so many times, ranging from the first African-American woman in space mission all the way to the first assembly missions of the International Space Station. And we're trying to see if there's a difference in the development and detachment of these whiskers under spaceflight conditions. And we were able to do this through the support of CASIS and NanoRacks and a variety of other sponsors financially. So my journey began in 2014. I joined a team with Joseph and Gabe, and we got the idea for tin whiskers from our mentors, and we began writing. And initially, Joseph and Gabe, I left the science to the boys, right? And I was helping with the actual writing. But the more we started working on this, and once we won, I started getting my hands dirty, I realized how incredible this was. I had never been interested in science or space, but the wheels started turning in my head, and I started thinking, maybe this is what I want to do with my life. And we were invited to speak at the Smithsonian, and I was 17. I had never spoke publicly before. I was shaking so bad I had to hold the podium at first, so you couldn't tell. But once we started talking about tin whiskers and the International Space Station, all that fear melted away, and I realized how genuinely excited I was to talk about these things. And I decided that day that I wanted to devote my whole career to this exciting era of space exploration. So we went down to our launch at Wallops Island, Virginia. We went to the end of this road. I took this photo. We were about 1.5 miles away. This is the Orbital 3 mission. The Orbital 3 did not get to the space station, as you can tell by this photo. We could see the flames devour the launch pad. We could feel the heat in our faces. And I can't explain how sad that was for us to see our work explode. But within 24 hours, we heard from CASIS, we heard from NanoRacks, and they told us, this isn't the end for you. You and all the other student experimenters, your experiments will fly again. We heard from our mentors, and they said, we're still here with you. Go and get some ice cream, and we'll talk tomorrow. Truly wise words. So, take 2, we decided to improve on our experiment and try again. Everyone else from our payload flew in SpaceX 6, but because we tried to use this failure as an opportunity for growth and improvement, we ended up on SpaceX 7. And SpaceX 7 also exploded. At this point, I was starting to think, maybe I have some bad mojo. And at this point, I first started thinking, maybe I can't do this again. Seeing something that I cared so much about and worked so hard on explode, literally twice before my eyes, I thought, maybe I can't do this. And I remember reaching out to our program director, Dr. Jeffrey Goldstein, an astrophysicist, and he said, Rachel, no one ever said exploration is going to be easy. And that's something that stuck with me continuously, and we decided, we've gotten this far, we might as well keep going. So sadly, I was the only tin whiskey available to go for the 3rd launch, but I am so glad that I did. Seeing our work finally come to fruition, it proved that everything we did was worth it. And although I never want to hear this phrase ever again in my life, the 3rd time was a charm. So looking back on all these experiences, I realized if it wasn't for the resilience of the scientific community and the support of organizations like NanoRacks, DreamUp, CASIS, and SSCP, we never could have done this, and it paid off for me in a way that I can't even explain. I'm from South Carolina. Believe it or not, almost no one I know left the state for school, and I was able with SSCP to get into the University of Chicago, not to brag, but the #3 rated school by News and World Report, and I could never have done that if it wasn't for SSCP. I am truly an ordinary student who's afforded an extraordinary opportunity, and this goes on all the time. Just 87,000 students in SSCP alone. That's astounding. And CASIS is continuously expanding their programs and making space more and more accessible. You have NanoRacks continuously sending student experiments to space, and DreamUp making space-based curriculum for students all over the world, actually. So I'm so grateful that they're doing this for people. Especially thinking on a quote from Carl Sagan, the dreams we give our kids are maps for the future. And I'm so glad that these organizations are out here doing this. Also, look at that chocolate alligator. That's P-dope. So I'd like to thank you for your time, and I hope you guys can get involved in space however you're interested in doing. And if you have any questions, you can reach out to me at limburg@uchicago.edu. Thank you so much.
Thank you, Rachel. Let's give Rachel a hand. It was awesome.
I'm going to hang on to this.
So there's another life lesson. It's not just about the life and physical sciences and trigonometry and the STEM. I think what we heard from Rachel, it takes a little bit of persistence as well, right? You got to.
I have a question. Can we do one more slime experiment?
We took away the experiment stuff.
No. Come over here. Here, I have an idea. So come to this kiddie pool over here. It looks like a kiddie pool. Yes, I get it.
Okay.
But it's actually a slime containment unit. So there's slime inside of this, cool contraption, which is not a kiddie pool. No, this is actually groundbreaking science right here. This is the coolest thing you'll ever see. All right.
Awesome.
So would you like to participate in the experiment?
I'd love to help you. What can I do to help?
Awesome. All right. Well, I'm going to have to ask you to remove your shoes and your socks.
Okay.
All right. So this slime actually tests the effects on feet. All right. Cool.
I'm glad I bought new socks. It could have been embarrassing.
Yeah, maybe roll up your pants a bit too. We don't want to ruin any clothes. Perfect. I like it. Awesome. Cool. Okay, just step inside. Yeah. Cool. Perfect. One at a time. Oh, yeah, get the other one in there too. Sweet. Feel around. No, not a swimming pool. Nope, it's groundbreaking science. Yep, it's a slime containment unit. Okay, so let's start with observations. So feel around. What do you observe?
Kind of squishy.
Squishy? Gooey?
Very cold.
Cold, cool. Well, next time maybe we'll heat it up, make it a little nicer warm. Yeah, feel around.
This is really slimy stuff.
All right, well, move your feet around.
It feels pretty cool. It's gooey between my toes. It's gross.
Gross.
But in kind of a good way.
Sweet.
It feels like it might be good for your skin, for your
Yeah, you know.
Pedicure, so I'm digging this.
It's like it takes off dry skin. Yeah, it's actually known to do that, right? It's like a massage. All right. Well, how do you think it would feel on your head? I liked it. Who liked that? Was it worth it?
It was well worth it.
Was it worth it?
Was the experiment a success?
You know what? It was. It really was. That was the best experiment we've conducted. Now, I have one more question.
Yes.
Do you think Nickelodeon would be able to slime astronauts in space?
There's one way to find out.
And that is?
Take it to space. And
Taking it to space. Thank you. Well, thank you so much. I don't think I want to shake your hand, but...
Give me a hug.
Oh. No, thanks. Well, thank you, everyone. Thanks. Thanks, Ken.
Thanks, everybody.
Bye.